So thanks very much to NetUK and the program committee for allowing me to do this presentation this morning. As James said, it's all about power consumption in metro optical networks. There was a brilliant presentation yesterday about power in data centers, but the access, the last mile, the bit to the customer location is still the hardest bit for any operator. Power is a cost, and we all know that as an industry we're using more and more power. Just a couple of reports that you can go and read in your leisure time about power consumption continually to go up. So my presentation today is to offer some insight and just make us all think a bit more about power and can we do it better in the metro optical network space. So a little network diagram, because it's a presentation, we've got to have a little network diagram. So on the left-hand side here we have some sort of switch, router, radio, where you've got some grey optics, 1310, 815 nanometer optics, into what most people consider to be a WDM system of some description, which has management cards and a chassis and fans, and a transponder card that takes the grey optic in, converts it to a colour, just got 4 little colours for this instance, and then sends it out over a WDM MUX. So when you talk about WDM, this is what most people consider to be a WDM system. This is what most people default to in terms of WDM. There's also just a slight variant on that, which is the MUX sponder, which again you have the switch router, on the left-hand side, or radio, grey optics. And in this instance, we're actually doing the MUX sponding on a line card that then takes that out over the network. And later on, I'll explain why I've split out transponding and MUX sponding, because they are slightly different. And then we've got what everyone's getting excited about, which is IP over DWDM. By the way, IP over DWDM is nothing new. It's been in existence for 20 years. The difference is, and this is an interesting thing we're seeing, is that when WDM first came out, people were really excited about 40-channel and 80-channel MUXes. We're now, and the reason being they wanted as many 1 gig or 10 gig services they could to send down that fiber. So 40 channels or 80 channels made absolute sense. With the advent of 400 gig and 800 gig optics, we're seeing people now just using maybe an 8-channel MUX, 8-channel DWDM MUX, because 8 times 400 gig is a lot of bandwidth, and the MUXes themselves are peanuts in cost. So IP over DWDM is being used more and more, and there's nothing wrong with mixing IP over DWDM with an active system on the same link. All WDM lambdas use the same, all vendors use the same WDM lambdas. So I'm moving ahead now, I'm looking at what we're doing here. So we looked at metro links, typically 10 to 80 kilometers. In Europe, it very rarely goes over 40 kilometers. If you're in a radio, if you're in a 5G world, it's 15 kilometers max because of the latency issues. So we're looking at the transport technology in terms of the power usage. We're not looking at the layer 2, layer 3 devices. We're not looking at amplifiers because this is short haul stuff. And we're comparing the power usage at 1 gig, 10 gig, 25 gig, 100 gig, and 400 gig. And it's a one-for-one service. So if you're doing transponding or MUX sponding, if it's 100 gig, we're looking at that 100 gig, even if it's going over a 400 gig service. So just a recap, at the top left, you have the grey optics, point to point, that works absolutely fine. You can do 1 gig, 120 kilometers, no problem. Then we got the passive WDM, the second row down, where you're talking about some colored transceivers. And then you've got the transponding one where you can actually see the increase in hardware requirements, and the muxponding, again, where you're seeing a huge amount of hardware that's required to do a muxponding or a transponding solution. So let's look at some power consumption now on some transceivers. At 1 gig, to 1 to about 2.5 gig, there's not a lot of difference between the data rate and the power usage. There is a slight increase when you start coming into colored WDM optics, because the colored WDM transceivers have some temperature controllers, but you're only talking about 1.6 watts or 1 to 1.6 watts. So at 1 to 2.5 gig, the power usage isn't a lot different, irrespective of distance. Temperatures make a difference, and I'll come on to temperature again in a minute. Temperatures do make a difference. We looked at 1,700 transceivers. 97% of the time, they use less than 50% of the specified power. So if you look at the data sheet, they're using 50% or less of the actual what it states on the data sheet. And I said that's 1,700 transceivers we looked at. 97% of the time, it's using a lot less power. So what does that mean in terms of your network? So at the yellow bar at the top that's what the data sheets say. There's a whole bunch of transceivers from SFP, some cheap SFP copper transceivers at the bottom, all the way through to some 10 gig ZR DWDM transceivers. Temperature has an impact on the actual power used. So the gray one is running at 85 degrees, the blue one is minus 25 degrees, and the orange one at the bottom is 25 degrees. So you can see there's a massive difference between what the data sheet states versus the actual power used. Now let's look at 100 gig and 400 gig. The power consumption there varies dependent upon the data rate. It also varies dependent upon the complexities of the transceiver that's used. And the COWI becomes very important. The COWI is the number of electrical lanes, and electrical lanes use power. There's no two ways around it. So you can see even a coherent, the one highlighted in red, there's two different types of coherent, 80-kilometer coherent transceivers. One uses 6, and one uses 23.6 watts. So it does really depend upon the data rate, and the different architectures within the transceiver can also make a huge difference to the power used. And the difference is down to direct detect versus coherent, and just a very simplistic diagram on that. At the top there, you've got the direct detect. It's a very simple architecture, whereas the coherent, and the main difference is the coherent has a DSP, and a DSP uses power. You have to power that DSP with something. It also contains a number of other functions as well, but a direct detect coherent is really simple. A coherent transceiver has a DSP and other functions, therefore the power usage is greatly increased. So just on the transceiver power, the data sheets state the maximum power, which can vary hugely from the actual power used. Temperature makes a difference. So on the slides I'm going to show you in a minute, the direct detect, that's 1 gig, 10 gig, 25 gig, typically consume 40 to 60% of the stated maximum power. We've assumed 57% in the models I'll show in a minute. The coherent transceivers, i.e. those greater than 100 gig coherent, because there are 100 gig direct detect as well, is around 75 to 90% of the datasheet power. And we used 87% in the models. Oh, drinking out of wet glasses last night, that's what this is. So some notes on the active power consumption. This is trying to measure across many different vendors, and it's virtually impossible. However, it varies greatly from vendor to vendor. But without doubt, the common themes on this is all of active systems have power supplies. They are not always, or very rarely are fully loaded, so you're using power even though the system itself perhaps isn't fully loaded. And an active solution, quelled surprise, an active solution will use much more than what we've done here in terms of our typical models, just trying to create some, it's difficult to measure across vendors, that's what I'm trying to say. Cooling, air conditioning. If you have product that needs cooling, it's very difficult again to work out what that cooling adds in terms of power usage. But a rule of thumb, and what we come up with is for every watt of power used for the WDM system, we've added a watt of power for the air conditioning. So we basically doubled it if you use cooling, or air conditioning, I should say. Here we go. So this is power consumption excluding external cooling, sorry. So on the bottom we have 1 gig, 10 gig, 25 gig, all the way up to 400 gig. The orange line is the passive WDM, using very little power. The green dotted line, this is where you start using coherent optics, and as you can see, the power usage then increases significantly. So again, keeping on the orange line, it uses about 10 watts for a 100 gig solution, going up to about 41 watts for a 400 gig solution. Important point to note is that a 400 gig transceiver will use less power per bit than 40 times 10 gig. So it still makes sense to use a 400 gig if the traffic requires it, because it will use less power. So we're not saying don't use 100 gig, 400 gig, 800 gig, wherever, if you need it. The yellow line is the transponding. So this is the power used when you're using transponding in your network architecture. And as you can see, you use about 7 watts for a 10 gig, goes all the way up to 211 watts for a 400 gig. And the blue line is the muxponding, which uses even more power because it needs more processing, therefore it uses more power. So onto the marketing bits. The transponding solution uses 4 to 5 times more power than a passive WDM. A muxponding solution can use 10 to 20 times more power than a passive WDM. My only comment on that is marketing statistics, but it's an indication, and you should think about how you architect your optical access networks. This slide is the same information, but now adding some sort of cooling or air conditioning, and we've more or less doubled the figures. So for a passive WDM solution, at 10 gig, it uses approximately 3 watts, same as 25 gig. Again, we've got that dotted line where we start going into the coherent optics, where we increase the power significantly. And again, you have huge increase in power usage if you start using either a muxponding or a transponding solution. So this is now the maximum as per the data sheets. So are you engineering your access networks based upon what the data sheets are showing versus what you're actually using in your access nodes? That could be a street cabinet, could be a POP. I know you've obviously got alarms with regards to looking at the heat and power used in the equipment at the street cabinet. But are you over-engineering what's required in your optical access network? I'll come back to temperature again. Temperatures, of course, will impact the reliability. So if you start running these systems hot over time, it's going to cause some problems. These things don't like running hot, just like me, don't like running hot all the time. You need to look at use of industrial temperature transceivers in these access nodes, because if they are running hot, you need something that's got extended temperature ranges. An active system will often use more power than you think, because if it's not fully populated, because you're still running those management cards, the power supplies, and the rest. So it can increase your power 4 to 5 times versus an active system, and you can make Excel spreadsheets say anything, right? It can increase your power usage by up to over 100 times. Great, what you can put into an Excel spreadsheet. So summary, power usage will continue to increase because we have to deliver more capacity, and the access network remains the most difficult piece of any network infrastructure. It can, in some scenarios, use up to 100 times more electrical power than technically necessary. And as was mentioned yesterday, power is becoming an increasing threat to the industry. Can we get enough power everywhere needed in the network? So passive technology, passive WDM, will significantly reduce power usage between a factor of 5 or 10. However, we don't suggest that you only use passive WDM. There's plenty of reasons why you might want to continue to use an active WDM system. If you, and there's nothing wrong with mixing passive and active WDM on the same link. There are many service providers who put a passive WDM system at one end because at their BBU hotel or the central office, they want high capacity, as much high capacity as possible. But the remote end, they might want to have a demarcation device. They might want a clear demarcation at the remote site. Or the other way around. We know people who do it the other way around, where you want to keep power usage as little as possible. And I come back to the same comment I make often. Every single optical vendor in a DWDM environment uses exactly the same lambdas. So channel 20 on our kit is exactly the same as channel 20 on any other vendor. The only thing that might differentiate is the insertion loss. Oh, one other thing with regards to passive WDM that I should have mentioned, and higher speeds, sort of 400 gig and 800 gig. If you were using passive WDM, demuxes in your network, make sure that the passband within those 100 gigahertz spaced DWDM systems are greater than 75 gigahertz passband, because some of the modulation techniques used on some of the 400 gig and beyond transceivers will create errors if you try running that through a standard 50 gigahertz passband interface. We're seeing requests for 250 gigahertz passband on WDM because of the 800 gig and beyond transceivers with the associated modulation techniques. So just make sure that if you're using passive WDM, any passive WDM you buy now, make sure it's got greater than 75 gigahertz passband. And finally, there's less power used. Therefore, if you are looking at your scope 3, then this is an ideal way to help you meet some of your CSR targets, because you can be actively seen to trying to reduce your CO2 impact. So, yeah, really think about how you're deploying your WDM systems. So I'm a little ahead of time. My name is Steve Jones. You can find me on LinkedIn, or just look for the Unicorn Farmer, because do you know how many Steve Joneses there are in the world? Well, I'm on about page 20, right, if you're looking for me on Steve Jones. The other thing I'd invite you to do is, on LinkedIn, we do a weekly, what we call brain snack. This is not about product. They're literally 3, 4, 5-minute videos about all sorts of stuff in the optical world. There's even some videos on there about beekeeping, because in HQ in Mainz in Germany, they keep bees. It's short videos to explain the technology. So, yeah, a little bit ahead of time. Does anybody have any questions? That's a no. Well,
hello, Steve. Dave Wilson from Glide, PC, whatever.
Morning, Dave.
Yeah. So a thing that I've seen as a trend in optical networks over the past however many years is that everything keeps getting smaller and more power efficient, and more things are starting to be put in the optical package that gets put into the switch, you know, the QSFP28 or whatever it is. Do you think there is a scope in which, you know, there will be fewer and fewer discrete optical platforms, and all the smarts will just be done in the thing you plug into the switch? Because, I mean, it used to be you couldn't get, you know, coherent in a QSFP28 package. Now you can. A bunch of stuff we've deployed. We did have, you know, big muxponder chassis. Now it's just passive chassis, and the smarts is in the optic. Do you see that as an ongoing trend?
Maybe. Yeah, if you go back to when the optics transceivers, a lot of them were onboard stuff. So you wanted long reach. Everything was on board, and you had to buy it from a specific vendor. Well, the advent of the pluggable transceivers, that went away, and now you have the MSA agreement, so multi-source agreement, so you can buy a transceiver from anyone, it'll fit. If we look at 400 gig, QSFP, DD, I'm sure the Flex Optics will talk about it later, is being used. 800 gig, is it OSPF? If it's OSPF, which version of OSPF? If we start looking at what now people are talking about 1.2, 1.6 terabits and beyond, is that going to be on board again? Because if we look at power usage, if you keep it all optical, it uses less power. So the more you can keep things optical, the less power you use. Therefore, would pluggable optics be the right solution for 1.6 and beyond terabits? We're already seeing data centers which are being deployed with all optical cross connects. So there's at the top of the rack is an all optical cross connect. So you're switching everything in light, because as soon as you start doing anything electrical, not only does it add latency, it also adds power. So the answer to your question is, I don't know.
Fair.
There's.
I would say yes.
There will become a limitation, and maybe we do go back to prepackaged optics on a line card rather than pluggable optics. But I come back to, and we as an industry, we're brilliant at creating new widgets, right? If you have an 8-channel MUX and you have 8 times 400 gig or 8 times 800 gig, that's a hell of a lot of bandwidth. That's a hell of a lot of bandwidth. How many companies really need 1.6 terabits today on one line card, right? Because that means you've got to have at least 2, because you need resilience. if you're carrying 1.6 terabits, you've got to have bloody resilience there somewhere. So, yeah, this is great. We're pushing the envelope and all this stuff, but well, sometimes simple is better.
That's fair. Thank you.
Any other questions? Thank you all very much.